Right. The first part of ionic equilibrium is little easier and more theoretical. So let us go it quickly. Writing work is less. Just understand the terms more. Uh, Whatever the terms that are used in this topic, those terms are important. So try to understand those terms carefully. Check. In ionic equilibrium, we are trying to explain the same reversible reactions which we learned in chemical equilibrium, correct? But here there should be ions involved in the product side. Then we say this is related to ionic equilibrium. Okay. In general, a substance which we add to any solvent is categorized into two forms. One is electrolyte, the other one is non-electrolyte. Electrolyte are those substances which will produce ions when you add it to water. For example, if you have NaCl, HCl, NaOH, if you add them to water, they will give you various ions. Na plus Cl minus H plus OH minus and so on. Non-electrolytes, which means they will dissolve in the solution, but they do not give any aqueous, they do not produce any ions in aqueous solution. For example, sugar, urea, proteins, they all will get dissolved, but they are not going to give you any ions as such. Okay. Within the electrolytes, we have two types of electrolytes. One is a weak electrolyte, the other one is a strong electrolyte. We use the term weak electrolytes if the dissociation of the substance is not more than 5%. Okay, from 0 to, I mean, from 1 to 5 percentage, that is the maximum amount of dissociation which you will notice. Okay, especially when you have weak acids, weak bases, and some sparingly soluble salts. If you have some sparingly soluble salts like calcium carbonate, for example, a chalk piece added to water, the number of ions that it can give is very, very less. Correct? But it will have a solid existence also. It will have ions existence also. So therefore, sparingly soluble salts, weak bases, weak acids. These are all the forms which you will notice in weak electrolytes. Okay. Next is strong electrolyte. So when it comes to strong electrolyte, it is about dissociation of substance more than 95 percentage. Clear? If the dissociation is more than 95 percentage, we call it as strong electrolytes. So you can see strong acids, strong bases, and highly soluble salts. All highly soluble salts like NaCl, correct, KCl, they will dissociate 100%. Then we also have terms like strong bases, strong acids, which we'll be using, which almost dissociate 95% and above. So these are called strong electrolytes. Okay. Next, let's understand what is Arrhenius acid-base theory. Clear? So basically, now we are trying to explain the definition of what is an acid, what is a base, right from the initial definitions to what is a modern definition. Okay, check. The first of the kind of acid-base definition which is given is by Arrhenius theory. That's why it is called Arrhenius acid-base theory. According to this theory, electrolytes, if they are giving H plus ions into the aqueous solution, then we call it as an acid. If they increase the H plus concentration in the aqueous solution, we call them as acids. And electrolytes, which increase the OH minus ion concentration, we call them as base. Okay, this is a very schoolish definition. I'm sure you all must have heard about this as well. Now, usual representation is like this: HA, or HX. If I write this way, that means I'm referring to acids. BOH or XOH, which means I'm referring to bases. Clear? Now see, if you have HA added to water and if it ionizes as H3O plus and A minus, that means we are writing about acids. So you can see HA aqueous will give you H plus aqueous plus A minus aqueous. BOH in aqueous solution, if it gives B plus and OH minus aqueous, that means this is an acid, this is a base form. Okay. Now, H plus when it is present in water, it can be simply shown as H plus, or an H plus will be tagged very strongly by hydrogen bonding with one water molecule. That means if you have H plus added to one water molecule, The lone pair present on oxygen will be so strongly bonding with H plus that it will always appear like H3O plus. In fact, there are cases depending on temperature. If the temperature is little lower, even water molecules, at least two water molecules can also be tagged with it. So you will appear this as H5O2 plus. If you go further lower temperature, maybe around 5 to 10 degrees centigrade, you will also have 3 moles being tagged to H plus, and you'll see this as H7O3 plus. So any representation is correct depending upon temperature timelines. Normally at room temperature, all the standard reference books use this as H3O plus, correct? But there is no harm in writing H5O2 plus, H7O3 plus, or even for that matter, H9O4 plus. All these representations are correct at different temperature timelines. Okay. Similarly, when it comes to OH minus also, you can simply show it as OH minus, which is the maximum way of showing at room temperature. But at room temperature, there is a small existence of OH minus as H3O2 minus, H5O2 minus, or H7O4 minus. Okay. These are all various representations, H3, H5O3 minus. Okay. Clear? So these are all the ways of representing, OH minus as well. Everybody understood? Next. What is the main limitation of the Arrhenius acid-base theory? Problem here is it is only applicable for aqueous solution. The minute you are explaining something for an alcoholic solution, some benzene solution, in benzene or in ethers or in acetone or in any non-polar solvents or anything which is other than water, even if it is polar, if it is other than water like alcohols, then you cannot apply this definition as Arrhenius acid-base theory. So Arrhenius acid-base theory is only applicable for aqueous solution. Okay. Also, according to the Arrhenius acid-base theory, a base is expected to give OH minus. But a lot of times there are bases which does not have OH minus directly in them. For example, ammonia. Ammonia does not seem to have a OH minus along with it. You cannot see any oxygen present on ammonia at all. But ammonia is a very good base. Okay, ammonia is used as a base in many solvents. So even though ammonia is a base, it is not accounted as per the definition as of Arrhenius base theory. Clear? So these are major drawbacks: representation of all forms of bases and representation of anything other than aqueous solutions. These two are the main drawbacks or limitations of Arrhenius acid base theory. Next comes Brownstein-Lowry acid base theory. According to Brownstein-Lowry acid-base theory, irrespective of the solvent, that means it is not necessary, it has to be always aqueous solution. Whatever be the solvent is, if a species, if an electrolyte is releasing H plus ions, which means it is an acid. And here we do not use the word H plus ions, we use the word proton. And you know that H plus is nothing but a proton, right? Hydrogen has one electron, one proton. If you remove the electron away, what is left now? Only proton is left. That's why H plus is read as proton here. So if in the solution you are releasing H plus, that means it is donating H plus, then the proton donor is called as the acid here. Proton donor is called as acid. On the other hand, if somebody is donating, the other one has to accept as well, right? H plus will always will work on this transaction that one is giving, one is taking. So the one species which is taking H plus, that is read as base. So H plus acceptor is a base, H plus donor is a acid. So proton acceptor is an acid, proton donor is a acid, proton acceptor is a base. Okay. Now notice, if I read this as an acid, for example, in water, I added HA in water. And if I read this as an acid, Brownstein-Lowry acid, that means I'm expecting this to give away H plus ions. So after releasing H plus ions, what is left now? It is remained as A minus. What happens to our H2O? H2O must have accepted that H plus. That means it is acting like a base. So the product will become H3O plus. So the product is H3O plus and A minus existing in an equilibrium. This is what happens as per Bronsted-Lowry acid-base theory. Now listen, according to Bronsted-Lowry acid-base theory, if there is an acid which is losing a proton, the rest of the adduct, that means rest of the part of the electrolyte, is called as the conjugate base. It is called as conjugate base. Similarly, if you have a base, after accepting H plus ions, the new species which is formed, it is called conjugate acid. Okay. So now Ha and A minus, H2O and H3O minus. So this is an acid, this is a base, this is a base, this is an acid. So this is called conjugate acid base pair. Okay. Remember it like CAB, CAB. CAB means conjugate acid base pair. Clear everybody? So whenever you use the word CAB, which means we are referring to a conjugate acid and its respective base on it. Clear? Notice this one. If I make a reaction like this, NaOH is a base, HCl is an acid. This we have learned it in school also, right? An acid-base reaction will make salt and water, correct? Now, if you put it in a ionic form, have you noticed there is no role of Na plus actually? Na plus on the reactants and Na plus on the product is present. It has no role. So remove that Na plus now. What is left? In that case, we have OH minus, HCl, Cl minus, and H2O. These are the products and reactants. So now this OH minus can be read as a Bronsted-Lowry base, which is accepting H plus from HCl and converting into a conjugate acid. So you can see OH minus is a base and water is a conjugate acid. Clear? Now in this particular example, water is an acid. In the above example, water is a base. Remember, so water is amphoteric, which means it can behave like both acid as well as base, depending upon the situation of the solution. Similarly, HCl is an acid here because it is releasing H plus and Cl minus is a conjugate base of HCl. So this is a cap pair, this is a cap pair. Everybody understood? So a chemical reaction as per Bronsted-Lowry acid-base theory is mostly to do with how a transfer of H plus happens. Okay, if there is an H plus transfer involved from one species to the other species, that means an acid-base reaction has happened. Okay, now given these examples, our objective should be about identifying which of them are conjugate acid-base pair. Correct? This is one very important task that has been usually asked. Now listen up. You always expect a conjugate acid-base pair to be the one where only one H plus is transferred. Don't see that if there are multiple H plus transferred, then we call it as conjugate acid-base pair. No. Conjugate acid-base should be always about one H plus transfer or one H plus acceptor. Okay. So notice one by one here. Which of them are conjugate acid-base pairs in this case? Check out. First one, HCl and Cl minus. Yes, definitely this is a conjugate acid-base pair. Correct. You can see this is an acid, this is a base. That's why it is a conjugate acid-base pair. Clear? Now here, this one is a base, this one is an acid because it is accepting H plus. So this is also a conjugate acid-base pair. Now here ammonia is an acid. This one is a base because it has lost H plus. But this can also be read as conjugate acid-base pair. Here ammonia is a base. In the third example, ammonia is used as acid. Okay. Like I said, depending upon the situation of the solution, one could be acid or a base. Likewise, if you compare these two, you can see this is an acid, this is a base because it has lost H plus. So this can also be referred as conjugate acid-base pairs. Next, this is an alcohol. Alcohol accepting H plus, then it will become OH2 plus. That means this is a base accepting an H plus, becoming an acid. So this can also be referred as conjugate acid-base pairs. Next, NaCl. In NaCl, Cl minus is a part which is always a base, but it doesn't seem to be like accepting something like, Cl here. So if it was HCl, then this would have been correct. But it is not Cl. So hence this is, although it is an acid, HBr is an acid, this is not a conjugate acid-base pair. Similarly, NaI in HCl is also not a conjugate acid-base pair. This is a base, this is an acid, but not together a conjugate acid-base pair. Okay. Next, H2SO4 and Na2SO4. Of course, this is an acid. It must have lost H plus two times. That's when you get, SO4 2 minus. But like I said, the immediate H plus acceptance is only called as, this is a base, but these are not conjugate acid base pairs. It should be immediate ones, right? For example, here, you notice this one. If you notice Na2HPO4. See, sodium is always an spectator. It has no role here. So if I remove the sodium part, it is actually PO4 3 minus. And here it is HPO4 2 minus. Correct? Now notice it carefully. If only this loses H plus, you will get PO4 3 minus. Correct? Hence, this is a conjugate acid-base pair in which this is acting like an acid, this is acting like a conjugate base. So I think fundamentally it is clear. When do we use the word acid-base, conjugate acid-base pair? Next, H2S and HS minus. So here it is clear. Now this is HS minus and then we have H2S. So definitely this is an acid, this is a base form here. So and this is a conjugate acid-base pair. Clear? Now here we have directly S2 minus and H2S. Then it is not a conjugate acid-base pair. Although it is an acid, this is a base, but it is not a conjugate acid-base pair. Now here it is 2 moles of Cn minus and barium 2 plus, you can use it as a spectator, that is not a part of acid-base reaction. And then we have HCN. So yes, it is a conjugate acid-base pair. So we have HCN, which is acting like an acid, and Cn minus, which is acting like a base. Okay, so this is an acid-base pair. So I suppose this part is clear, everybody. Each of these is acting like a conjugate acid-base pairs. I hope everybody understood this part. Shall I go ahead? Right. Notice. Usually, whenever you have a conjugate acid base, so one thing you need to realize is a strong acid will always give a weak, generates a weak acid in a reaction. Whenever there is a chemical reaction happening, we always expect the direction of the reaction is always from strong acid towards a weak acid. Weak acid giving a strong acid is not a good reaction at all, which means the reaction will be mostly held in the backward direction. Okay. Similarly, a strong base will generate a weak base, but weak base generating a strong base is less likely to happen. Second thing, whenever a strong acid is taking part in the reaction, its result will always be going towards weak base. The conjugate base which it will create is always a weak base. Okay. Similarly, if you have a weak acid, it is going to generate a conjugate strong base. And same logic applies for bases also. Okay. So what I'm trying to say is if you have weak base, then it will become a conjugate strong acid. It will give you conjugate strong acid. Similarly, if you have a strong base, you will get a conjugate strong conjugate weak acid. This is how you will generate reactions. For example, what I'm trying to say, this is the list of strong acids that you need to remember. Okay, everybody, this is a common list of acids. One is HCl, HBr, HI, H2SO4, HNO3, HClO4. If you see this as H3O plus, NH4 plus, ROH2 plus, or simply H plus, any of these, if you find it, right, you always refer them as strong acids. Okay, these are all strong acids. As if these are the strong acids, what could be the list of weak bases? right? Because these are all strong acids. So just write their conjugate bases, everybody. Cl minus, Br minus, I minus, HSO4 minus, SO4 2 minus, okay? NO3 minus, ClO4 minus, H2O, NH3, ROH. These are all going to be weak bases. So water, ammonia, alcohol. Everybody notice the last three. What are these? Water, alcohol, ammonia, and alcohol. Correct. These are generally, weak bases. In fact, I can add one more term here, RNH2, which will become RNH3 plus. When it is in a conjugate acid form, that is a stronger acid. But if you write its respective base, that is RNH2, it is a weaker base. Amines, these are amines family. Amines, alcohols, ammonia, and water. All of these are weak bases. Clear? This list you have to definitely remember, everybody. What is the list of strong acids? Okay. Now coming to the list of weak acids. Now rest of the acids whichever we find in general in inorganic and organic, they are all weaker. For example, first one, boric acid. This one is boric acid. BOH thrice, boric acid. I'm starting from a group 13 onwards. I'm going towards 17. You see, group 13, you will have one acid, that is boric acid. In group 14, we have carbonic acid and silicic acid. Silicon will have one acid, which is called silicic acid. Carbon will have one acid, which is carbonic acid. These are group 14 acids, everybody. In group 14, these are the two acids you will find. Group 15, you have a lot of acids, HNO2, nitrous acid, H3PO2, H3PO4, H3PO3. These are all phosphoric acids. All of them are weak. So in group 15, these are the ones which are very commonly used acids. Group 16, we have H2SO3, H2S. These two are weak acids which you will notice. Group 17, HOF, HOCl, HF, HClO2, HOBr, right? HClO3, all of those are weak acids. These are all weak acids. Next, inorganic acids, carboxylic acid, alcohol can also be used as weak acids, water can be used as weak acids, ammonia can be used as weak acids. Have you noticed something? These three, I have used them as weak acids also, as well as weak bases also, isn't it? So these three are amphoteric acids, acid bases. Okay, amphoteric means which has both behaviors. Okay, so I'll just mention that wording here. These three are amphoteric. Next, HCN. HCN is also a very weak acid. Alkanes, alkenes, alkynes, and phenols. All of them can be considered as weak acids. They're all very weak acids, but yes, irrespective of how weak they can always be subjected as weak acids. And now, putting all of their conjugate bases now, check out. If at all we convert them into their conjugate bases just by removing one H plus. So start removing one H plus in all of the cases. If you remove one H plus here, you can see H3O, HCO3 minus, CO3 2 minus, SiO4 4 minus. After removing four hydrogens here, removing one hydrogen here, one hydrogen here, two hydrogens here, three hydrogens here, you know, removing two hydrogens from here, one hydrogen, two hydrogens, one hydrogen, one hydrogen, one hydrogen, like this. If you keep on removing all the one hydrogens here, what is the rest form? These are all strong bases. Okay. So if you could understand how to generate in a sequence what are the weak acids and weak acids and strong acids, then understanding weak bases and strong bases is very easy. Okay, clear? Because it is just about conjugation. Strong will become weak, weak will become strong. Okay, my suggestion is once the session is done, today or tomorrow, whenever you get time, write on your own and try to see how many you can recall. Okay, Try to recall all the weak acids and strong acids. First write them, then convert everything into their conjugate forms. So you can get the bases also. Okay, this is an important practice, everybody. You must do it. Okay. Now, notice when you have H3PO4, for example, check this out. If I write this as HX, okay, if I write some acid as HX, it is called monoprotic acid. Monoprotic acid. Monoprotic means, protic means the one which is generating proton. So how many protons it can give? One proton. So therefore it is called monoprotic acid. If I write this as H2X, that is diprotic acid. If you have H3X, it is triprotic acid. And if it can give any n number of H plus ions, it is called polyprotic acids. Okay. So if n is greater than 1, correct? That is called as polyprotic acids, everybody. These are all polyprotic acids. If it is n is equal to 2, it is diprotic, triprotic, tetraprotic, and so on. Clear? So now have you noticed H3PO4? H3PO4 is one polyprotic acid. Okay. When it comes to H3PO4, notice one thing. After removing one H plus, what is left? We will have H2PO4 minus. Please listen to this reading carefully, everybody. This is a weak acid. Barabar? A weak acid is expected to generate a strong base, correct? So yes, H2PO4 minus is a strong base, no doubt about it. Okay. But at the same time, this strong base also still holds lot of protons on it. That means it can still act like an acid, correct? But releasing H plus from here becomes very difficult. Why, Imagine like this. H2PO4 minus is there and you are trying to release one H plus out of it. So that means it will become H plus, correct? Now you notice what would happen. Already it is a negatively charged. Removing a positive charge out of it becomes extremely difficult because H plus will be strongly attracted back towards this. So the reaction will move towards backward, correct? Which means extracting H plus, that means extracting proton out of H2PO4 minus is very difficult, correct? Everybody understood? It has a strong basic character, but if it has to act like an acid, it has to be a much, much weaker acid, understood? So remember this, in polyprotic acids, if the first acid is weaker, the second acid becomes much, much weaker than that. So that is why I've written it as WWA, which means weak acid. That's a very weak acid. Okay. And imagine if it has somehow lost H plus and we have generated HPO4 2 minus. Now, guys, if you are getting an base from a very weak acid, so what should it become? It should become strong base. So SSB here represents very strong base here. Got it? Similarly, if this is a strong base, imagine losing one more H plus out of it. This strong base refers to that as a very weak acid. Now, this such a weak acid, if it further loses H plus, what should happen to the base now? It should become extremely strong base. So it is strong base. So phosphate is a very strong base, everybody. PO4 3 minus can be used as a very strong base. So you can see basic strength wise, if you notice, PO4 3 minus, HPO4 2 minus, H2PO4 minus. This is the basic strength. And when it comes to acidic strength, H3PO4, H2PO4 minus, and HPO4 2 minus. This is the acidic strength which we have. Okay. So this one is a basic strength. This one is an acidic strength which we have. Clear? I suppose this part is clear, everybody. How do we read on the amphoteric cases? Very important. You should know which one is stronger and which one is weaker here. Clear? So I have written the same logic here. You can see NH4 plus, losing one H plus, it will become ammonia. Losing one more H plus, it will become amine. This is called amine. Losing one more H plus, it is called imine. One more H plus, it is called nitride. See the names, okay? So I'll write all the names also. The first one is called as ammonium. Ammonium. Ammonium ion is an acid. Second one is simply ammonia. Ammonia. Okay. This one is read as amide. This one is read as imide. Imide ion. This one is read as nitride. Nitride. Okay. So check out their strengths now. When it comes to basic strength, N3 minus stronger base, then NH2 minus, NH2 minus, and ammonia. Acidic strength, NH4 plus is stronger acid, then ammonia, then NH2 minus, then NH2 minus. Got it? So when you have polyprotic acids, if you have multiple H plus ions, how to lose, as you lose H plus, what happens to the basic strength? So I think you got an idea there. Yeah. Next. If you are comparing the acid base strength from left to right in the periodic table and down the periodic table, let's see what you need to realize. So first, if you are going left to right in the periodic table, everybody, if you are going left to right in the periodic table, check it out. Always compare electronegative difference first. We always need to compare, everyone, electronegative difference first. Okay. So if the electronegative difference increases, acidic strength will increase. Listen up. Any property that is explained in periodic table from left to right is always on the basis of electronegative difference only. Bond length, bond energy, bond order. Okay. Whether it comes to acidic strength, basic strength, everything is explained on the basis of electronegative differences. More the electronegative difference, acidic strength will increase. Okay. And basic strength, as usually, it will decrease when it comes to oxides. When you have oxides, they will show basic strength and that will decrease. Now, notice if you compare methane, ammonia, water, and HF, okay, then we have HF here. So, left to right, this is from group 14, 15, 16, 17. Group 14 to 17, if you compare all the hydride, these are called hydrides. So, if you compare the hydrides, HF is the strongest acid. Okay, because you are going from left to right, electronegative difference is more. Got it? Similarly, if you compare the same SiH4, PH3, phosphine, H2S, HCl, which one should be the strongest acid? Left to right, acidic strength should increase, everybody. Clear? Next, down the group. When you are going down the group, then you will only compare size or bond dissociation energy, everybody. Remember, bond dissociation energy is the most important factor whenever you are going down the group. In periodic properties, every property down the group is explained on the basis of bond dissociation energy. So, if the bond dissociation energy increases, acidic strength decreases. And you know what happens down the group? Down the group, size increases. Okay. Top to bottom, when you go, size increases. If size increases, bond dissociation energy decreases. If bond dissociation energy decreases, the acidic strength of hydrides increases. So that's why if you compare HF, HCl, HBr and HI, HI is the strongest acid, everybody. HI is one of the strongest acid. This is from group 17. In group 16, tellurium, H2T is the strongest acid. Then H2SE, H2S and H2O. These are the strongest acids. Clear? These are all the acid forms. Now the same logic, if at all I remove one H plus, then they all will become bases. Correct? Now see the bases here. If this is a very weak acid, what should happen to its conjugate base? It should be the strongest, right? So therefore, when it comes to basic strength, this is the basic strength now. CH3 minus is the strongest base. Then silicon is the strongest base, then phosphine, then sulfine, then sulfide, then chloride. Similarly, if you have F minus down the group, you can see acidic strength was increasing. So now the basic strength should decrease. OH minus is a strong base compared to the others. Okay. So quickly go through it once. Everybody, please check if you have understood how to realize the case from left to right and down the group. If anyone has any doubt, they can ask me. Anna, everything is clear, beta?
Yes, sir.
Ayushi,
Yeah, sir.
Shauri, Shauri, could you please respond? Shauri, if you can't respond, put a message, beta. Saida, did you understand this cases, beta? Left to right down the group.
Yes, sir.
Tanish,
Yes, sir.
Radhika,
Yes, sir.
Pratisha,
Yes, sir.
right. Now let's understand the third theory. Okay, this is most generic theory. So far, we have discussed Arrhenius acid-base theory, Bronsted acid-base theory. Next, let's see Lewis acid-base theory. Okay, according to Lewis acid-base theory, any species which accepts a pair of electrons is called as an acid. It should accept a pair of electron, not single electron. It should always accept as a pair of electron. Achha, if it has to accept a pair of electron, that means it should have one empty orbital. It could be empty p orbital, empty s orbital, empty d orbital, but it must have an empty orbital. Keep that in mind. Okay. Then those we call it as Lewis acids. Any species which donates a pair of electrons, we call them as Lewis bases. We call that as Lewis bases. Okay. It should have a lone pair on it. If you have one lone pair on a species, it can act like a Lewis base. So you can see ammonia has a lone pair on it. BF3 has an empty p orbital. So the lone pair can give donation to the empty p orbital, thus making a coordinate covalent bond. And if you recall, this is the one thing we learned in chemical bonding also. In chemical bonding also, we learned coordinate covalent bond is a result of attachment between Lewis base and Lewis acid. Okay, Lewis base is giving the electrons, Lewis acid is accepting the electrons. So that's how we get the coordinate covalent bond, which is the adduct between acid and base. Okay, so now notice Lewis acids must have an empty orbital. They must have an empty orbital, which is if you have H plus, BF3, BCl3, AlCl3, BeCl2, CH3 plus, these are all empty S and P orbitals. These will have all empty S and P orbitals. Next, PCl5. Now, if you notice all of this, their octet is incomplete. The first sequence, their octet is incomplete. They have either empty S or P orbitals. The second one, actually, octet is complete. In fact, the octet is expanded also. But yet, they have an empty d orbital. PCl5, POCl3, SO3, SOCl2, SBF5, SBCl5, AlCl5, SF4, all of them has empty d orbitals. Empty d orbitals is also a very good source to accept the electrons. In fact, any positive ions, if you have metal ions, they all can act like empty orbitals, right? They all will have empty s orbital or a p orbital or a d orbital. They can act like Lewis acids. Clear, everybody? So all of these, in fact, any oxides like SO3, even SO2 also, SO2, SO3, P4O10, right? In fact, all other oxides also I'll write down. So if you have P4O10, correct? Cl2O7, okay, SO2 also, TeO3 also, tellurium trioxide here, N2O5, clear? So all of these oxides can also be regarded as, Lewis acids. They can accept a pair of electrons. Next, if you compare, typically a complex formation in Lewis acid, sorry, not N2O5, because N2O5 does not have empty orbital. My mistake. Next, check out. Typically, if there is a complex formation, that is always a Lewis acid and base combination. For example, cobalt plus 3 is there. It is been combined by 6 molecules of water. So that means every water molecule which has a lone pair is making a coordinate covalent bond with cobalt. So what is this? It is like an acid-base connection. Hence, a complex formation. This is called as a complex, holding a plus 3 charge on. So this complex form is also an acid-base reaction. So one is a Lewis acid, the other one is a Lewis base, forming a complex. Okay. So complex formation is also a Lewis base relation. Okay. Lewis bases, anything which carries lone pair, simple. If they carry lone pair on the central atom, chances are they can act like Lewis bases. So you can see water, ammonia, amines, alcohols, anything which is minus charged. Okay, H minus, RO minus, CH3 minus. Okay, even H minus. I forgot to write that. H minus. Okay. So NH2 minus, RO minus, CO minus, and all the halogen forms, correct? All halogens, O2 minus, S2 minus, N3 minus, N3 minus, P, uh, P3 minus here, N3 minus here, like this. These are all going to be Lewis bases because they have an lone pair carrying with them. Okay. So this becomes very generic definition. See, what were the typical drawbacks of Bronsted acid-base theory? In Bronsted acid-base theory, we could never account for BF3 as an acid, correct? Can we say BF3 is an acid? Because it does not have any H plus. It cannot give any H plus. So we cannot call it as a Bronsted acid, isn't it? So anything which does not carry H plus, we can never say they can be acids, according to Bronsted acid-base theory, correct? So that is a major drawback. The major drawback is that explanation is only on the basis of proton transfer. While Lewis acid base is nothing to do with proton transfer, it is always to do with acid base. It is always to do with the lone pair transfer. So lone pair transfer not necessarily always have to have with respect to uh, any H plus or OH minus. It can be from any species. You can always have some lone pair or an empty orbital which can accept. Okay. So I guess Lewis acid base part is clear, everyone. Now, check out about water, everybody. See, whenever we talk about water, a pure water will always have very small composition of H plus and OH minus in its own solution. So if you take a pure water solution, you might also find a small composition of H plus and OH minus ions. So they will establish an equilibrium with water here. Okay. What did we learn from equilibrium constant, chemical equilibrium? That an equilibrium constant can be written in terms of products concentration by reactant concentration. So you can see H plus OH minus by H2O concentration. Now, generally, density of water is always 1 gram per ml. Correct. Now, 1 gram per ml as in 1000 gram per liter. Correct. So 1 liter has 1000 grams here. So which means if at all I have to write the molarity, what will be the molarity in that case? So molarity of water is number of moles by volume. Number of moles is how much beta? Number of moles is 1000 divided by 18. That will be the number of moles divided by 1 liter. So how much is the concentration? Remember this. This is very important information. The concentration of water is always 55.5 molar. Clear, everyone? Concentration of water is always 55.5 molar. Okay. So if you know the concentration of water, Correct. We assume that H2O is almost constant. For such high concentration, if at all there is a minute change in it, will it make any difference? Not much. That's why we always assume that the concentration of water remains constant. Okay, so if H2O is a constant concentration, Kd, the dissociation constant, which we have written just now, Kd is a dissociation constant, which is product concentration by reactant concentration. Can I say that Kd into H2O will almost remain constant all the time? And that new constant is called as Kw, which we call it as ionic product of water. So Kw is a product of two ions. You can see H plus into OH minus ions. Now, experimentally, Kd was calculated. Okay, you can use conductometric titrations from electrochemistry. You can use that experiments to calculate Kd value. So Kd value can be calculated from there. And if I equate that Kd value, you know the water concentration is 1000 by 18. And this is 1.8 into 10 raised to power of minus 16. So if I multiply that, I'm getting the Kw value as 10 raised to power of minus 14. So this is a constant value at 25 degrees centigrade. So remember, at 25 degrees centigrade, the ionic product of water is 10 raised to power of minus 14. Okay. So remember, ionic constant of water or ionic product of water. These are the terms that are used. Okay. And it is measured at 25 degrees. In throughout the chapter, we are not going to change temperature here. We'll take the calculation, everything at room temperature only in this chapter. Okay. So Kw is equal to 10 raised to power of minus 14. Now listen, all ionic dissociations are exothermic reactions because they are forming ions. So do you think ions are usually stable? No, they will again come back and try to go back to the reactant. But you are forcefully providing heat to increase the ion concentration. So which means unless the heat is provided, you cannot expect more products, more ions to form. Therefore, it is an exothermic change. So ionic equilibrium is always exothermic. If it is exothermic, the equilibrium will increase. I mean, it will go towards product as the temperature is increased. This is what we learned from Van 't Hoff's equation, correct? Recall from chemical equilibrium. As the temperature increases for endothermic reaction, reaction will go in the forward direction. So therefore, if at all you measure at ionic product as 87 degrees, the same ionic product is found to be 10 raised to power of minus 30. Okay. Earlier, notice here, when H plus and OH minus concentration are 10 raised to power of minus 4, if at all I take this as X into X, because H plus and OH minus concentration will be equal in water, so that is equal to 10 raised to power of minus 14, which means concentration of H plus is equal to concentration of OH minus is equal to 10 raised to power of minus 7 at 25 degrees centigrade. But if you take out the same thing at 87 degrees centigrade, now the same concentration is changing to 10 raised to power of minus 6.5. Both will be equal, but now the value of that H plus concentration or OH minus concentration has increased. Everybody understood? Okay. Every ionic equilibrium is an endothermic reaction. Keep that in mind. Next. At constant temperature, Kw and Kd value remains constant irrespective of addition of acid, base or a salt. That means whether you take an acidic solution or a basic solution or a salt solution, as long as it is an aqueous solution, the Kw and Kd value remains constant. Okay. Right. Next. This is an important term that you need to learn. What is potent of H plus and OH minus ions? What is the potent of H plus and OH minus ions? See, mathematically, we can write pH is equal to minus log of H plus ion concentration. pH is minus log of H plus ion concentration. Okay. So check out H plus ion concentration is 10 raised to power of minus 2 if at all I have it. Then pH value will be minus log of H plus ion concentration, which is 2. Now pH is 10 raised to power of minus 3, then pH is 3. Did you notice something? As the H plus concentration is decreasing, the pH value is increasing. So remember, pH value is inversely proportional to H plus ion concentration. Higher the concentration, lower the pH value. Okay. Similarly, we can have POH also. POH means minus log of OH minus concentration. Similarly, I can have PKW also, which means minus log of KW value. So as the OH minus concentration decreases, POH increases. As the KW value decreases, PKW value increases. Okay. So I think the potent values are clear. Mathematical implication of pH, POH, and pKa. Now, notice for an aqueous solution, we know that ionic product is H plus into H plus multiplied by OH minus. If I take minus log on both sides, then it will become minus log of Kw minus log of H plus minus log of OH minus. And by definition, this is pKw is equal to pH plus POH. Okay. So pKw is pH plus POH. pKw value we learned it is constant, which is 14. Therefore, pH plus POH is equal to 14 at 25 degrees centigrade. Same thing, we have just H plus into OH minus is 10 raised to power of minus 14. The same thing I have written in terms of pH and POH. So remember, in aqueous solution, this will always remain constant. As long as it is an aqueous solution, ये दोनों का sum हमेशा 14 होना चाहिए. Okay. Now listen, for an acidic solution, if you are using something as an acidic solution, which means we expect that the H plus concentration in the solution should be greater than OH minus. Okay. So if H plus is greater than OH minus, you know that if pH is greater than POH, but the sum has to be 14. So pH का value क्या होना चाहिए बेटा? The pH value has to be less than 7. Okay. And POH has to be greater than 7. Got it? And pH value of the solution should be greater than 10 raised to power of minus 7. Then the solution is acidic. Similarly, if the OH minus concentration is greater than H plus concentration, then the pH has to be greater than 7. Here, let me write down POH also for your reference. POH has to be greater than 7. And OH minus of the solution should be less than 10 raised to power of minus 7. Similarly, here, POH has to be less than 7 and H plus concentration has to be less than 10 raised to power of minus 7. Then we say solution is basic. For a neutral solution or a pure water, if you say solution is neutral or if you say solution is pure water, that means we expect H plus and OH minus concentration should be equal and it should be 10 raised to power of minus 7. So that means when pH or POH is equal to 7, then we say it is a neutral solution. Okay. Have you noticed something? At 87 degrees Celsius, we found that Kw value is 10 raised to power of minus 3. So for pure water, pure water, what is the pH value at 87 degrees Celsius? So pH value will be equal to 10, pH value will be equal to 6.5, which is also same as POH value. This is for 87 degrees Celsius. Similarly, for acidic solution, at 87 degrees Celsius, what should be the pH value? pH has to be less than 6.5. Now you do not see the scale as 7. Now you have to check it out 6.5. So pH should be less than 7. POH has to be greater than 6.5. Similarly, for basic solution, if you are operating at 87 degrees Celsius, then pH has to be greater than 6.5 and POH has to be less than 6.5. This is what is, 80 at 87 degrees Celsius. This is the standardization which you need to do. At 25 degrees Celsius, 7 is the standardized value. Based on that, you will have to judge acid, base, or salt. Okay. So I think the basic terms are clear, everybody, right? Let me close it with a last thing. What is Oswald's dilution law. Sorry, Oswald's dilution law. See, any weak acid, correct? More the dilution, more is the dissociation. If you have more the dilution, then it is more is the dissociation in that case. Clear? How do we prove it? Let's try to understand that, and we'll also prove the same here. So, how much is the dissociation in these cases? Clear? See, any weak acid, any weak acid, more the dilution, more is the dissociation. Check out. If you have a weak acid like HX, we expect that it will ionize as H plus and X minus in the aqueous solution. So what will be its Ka value? What is Ka means? Ka is the equilibrium constant defined for acid. So that is called ionization constant. Ionization constant. Ionization constant of acid. Since we are defining it for acid, that subscript A is used. Okay. Now, if you take this HX here, clear? Now imagine initially when time t equal to 0, that means before dissociation. Before dissociation, the concentration is C naught. And after it reached equilibrium time, let's say it has lost some x units from here to form x and x units here. And if you recall, degree of dissociation, degree of dissociation from chemical equilibrium, we learned alpha is equal to amount lost, amount that is lost by amount initial. How much is the amount initially we had? So in this case, the amount of solution concentration lost is X and the initial concentration is C naught. So X can be written as C naught alpha. So let me write down that. So C naught minus C naught alpha. This will be C naught alpha. This will be C naught alpha. Correct? Now the same Ka, if I write that, which is H plus into X minus by Hx concentration, that will become C naught alpha multiplied by C naught alpha divided by C naught minus C naught alpha. So C naught, one of the C naught is coming common. So it is C naught alpha square by 1 minus alpha. This is the value of Ka what you will get. Okay. Now we got this as Ka is equal to C naught alpha square by 1 minus alpha. And you know that for a weak acid, for weak acids, we expect that alpha is very, very small value. We expect in most weak acids, not all of them, but yes, in most weak acids, a generic weak acid, we expect the dissociation constant or degree of dissociation is very, very small value. So in such is the case here, we can say for this equilibrium, we can ignore, alpha value. So we can ignore this alpha value. So in front of one, it will be smaller value. So we can write it as C naught alpha square. So which implies I can write alpha is equal to under root of Ka by C naught. Correct? We can write alpha is equal to under root of K by C naught. Now read this properly. If you read this here, you can see if the C naught concentration increases, what is happening? Alpha value is decreasing, which means dissociation of acid decreases. Dissociation of acid decreases. Okay. But if at all you have decreased the concentration of C naught, which means you are doing dilution, correct? That implies you are doing dilution. That means whenever you dilute something, which means you are decreasing the concentration. So on decreasing, what is happening to the alpha value? It is increasing, which implies dissociation of acid increases. Dissociation of acid increases. So this is what we call it as Oswald's dilution law, which means according to Oswald's dilution law, as the H plus value, as the concentration value increases, as you keep diluting the solution, concentration decreases and the alpha value will increase. Okay. Now, what about H plus concentration from here? I can write H plus concentration, which is equal to C naught alpha. So C naught into alpha value we just calculated as Ka by C naught. So if I take C naught inside, it will become Ka multiplied by C naught. Okay. Now take minus log on both sides. So we'll get minus log of H plus concentration is equal to minus log of, what is this root? Root is nothing but the C naught whole raised to power of half. Okay. So I can get that half outside. So half outside into minus log of Ka and minus log of C naught. And minus log of Ka can be written as half of pKa minus log C naught. So this is the formula we'll be using a lot of times to calculate the pH of the acidic solution. So this is the formula we'll be using for calculating the pH of weak acid, everybody. Okay. So derived out of Oswald's dilution law, pH of a weak acid is always equal to half of pKa minus log C naught. Done. I want you to go through it once quickly. If possible, make a note of it. Done, everyone? Right. Okay. So we'll stop it here.